Welcome back to another Algebra 2 video. I'm Mr. Hibble. Today we're going to be talking about some sequences. This is our 7.4 notes. It's focused on geometric sequences, but let's go ahead and look at two types of sequences, or define two types real quick. A sequence, first thing you should know, is just a list of numbers, right? For example, you might have a list of numbers like 10, 14, 18, 22, ... It just continues. Well, if that list of numbers is made by adding or subtracting the same value, that is what's known as an arithmetic sequence. Whenever you add that same value and over, you get what is known as a common difference. For example, the list of numbers I just made, each term differs by just 4 values. You could add 4 between each of the terms to find the next one. For example, if we wanted to continue this list, you could add 4 to 22 and get 26. You could add 4 again to continue the list and get 30. The common difference in this case is plus 4. The other type of sequence that we're going to be looking at is what's known as a geometric sequence. A geometric sequence, again, is a list because it's a sequence. But this type of sequence is made by multiplying. Realize you might multiply by some fraction that can make your values get smaller, right? It's a similar idea to dividing. A sequence that is geometric might look like this, maybe 2, 4, 8, 16, ... right? The process continues. But what you would notice about each of these terms is they are found by multiplying the prior term by 2. So if I wanted to continue this process and find what comes after 16, I could continue the pattern. I could keep multiplying the value by 2. 16 times 2, 32 times 2, and again, the pattern just repeats. In this case, whenever you're talking about a geometric sequence, whatever the multiplicative rate is, that is known as your common ratio. In this case, our ratio is times 2. The reason we're talking about geometric sequences is they're very similar to exponential equations. Remember, exponential equations have a change that is multiplication as well, right? We have an exponent on it. That gives us that change. The base of your exponent is what we are finding with these ratios. That's why this table here is going to have very similar properties to exponential equations. For example, if r is greater than 1, if the ratio is greater than 1, just like if the base of your exponent is greater than 1, that would mean your function, your exponential, would be increasing, or your sequence would be increasing. Remember, when the base of an exponent is greater than 1, that meant you had exponential growth, right? Your graph would be increasing. Same idea if your r value, if the ratio is between 0 and 1 then. If it's between 0 and 1, that would mean your function is decreasing. Just like when the base is between 0 and 1, that meant that we had exponential decay. It was going down in value. We can also have sequences. This is where it's a little bit different than an exponential. We can also have sequences that have r being negative. R is less than 1. And what that would mean is every time you multiply by some negative, the sign would end up changing. Okay? In order to find a common ratio, one thing we can do, a very simple, a very quick process to find the ratio, is you always take the second term and divide it by the first. That's what this little subnotation on the G represents. It's the first and second term. So what we can do is we can find the ratios between terms to see if they are geometric. A geometric sequence would mean that the ratio between each of the terms is the same. It is common. So we could go ahead and start creating the ratio between consecutive terms. The second one over the one before it, I'd find a ratio of 3. But if I want to figure out if this sequence is geometric, I need to check the other ones as well. 15 and 6, the second one over the one before it. I could even check 30 over 15. What I notice is each of these values is different. When you get different ratios, what that ends up telling you is it is not a geometric sequence. There must be some other pattern that is occurring. You could use that same sort of process for number 6, but we're going to go ahead and skip to number 7 now. Number 7, let's check if it's geometric. Again, second term over first term. Divide it out, see what it gives you. You might call this 0.5 instead of 1/2. Those are equivalent. Check the ratio between 100 and 200. Check the ratio between 50 and 100 as well. Notice all three of these ratios, whether it's 1/2 or 0.5, they end up being the exact same. That tells us this is a geometric sequence. Geometric sequences have a common ratio. You would multiply by the same thing when you go term to term. That's what this division tells us. When we look at number 8, though, and number 9, this process is a little bit different because I'm not checking to see if it's geometric. So I don't need to divide each of the terms. What I do need to do is identify the common ratio. Notice they're already saying the ratio is common. So if I did all of the division like we did before, the numbers will give me the same thing. So I don't have to divide all of them. I just need to find the ratio. I just need to do the division once. When you do that, again, second term over the term before it. -2 over -1 gives us a ratio of 2. What that tells me is between each of these terms, we are multiplying by 2. -1 times 2 is -2. -2 times 2 is -4. Continue the process now. Continue multiplying by 2 to create this problem. And as you continue multiplying by 2, you end up filling in what those 3 missing terms are. Let's go ahead. Let's look at number 10. Number 10, right below it, what we need to do is, again, find the ratio and figure out what that might be. Second over first when you do it. In this case, that gives us -0.25. You could call that -1/4. Either of those is fine. They are equivalent. And again, that means that is the value we multiply by. 0.25 multiplied by -0.25. And we continue this multiplication. Okay, that looks a little sloppy there. I'm just going to get rid of it. I need to continue this. I need to continue multiplying by -0.25. Realize you're multiplying by a negative. If you multiply by a negative, we said that means we have an alternating sequence. That means the signs are going to be changing between terms. Our signs went positive, negative, positive, so then I would have negative, positive, negative. The signs must alternate. As you multiply it out, 32 times -0.25 gives us -8. Do your multiplication again, times -0.25. That would end up giving us +2. And if you did the multiplication one more time, times -0.25, you would end up getting a value of -0.5 or -1/2. If you need to find the next 3 terms, find the ratio and figure out the pattern. You know the pattern, you know the ratio, continue to apply it. The other thing you can start to do with geometric sequences is you can start to make an explicit formula. Some people like to use A for the explicit formula. I'm going to use G for geometric instead of A for arithmetic. We know there's 2 different types of sequences. What an explicit formula does is it allows you to find any term in the sequence. It allows you to find the nth term in the sequence. Few things to note. Whenever you have that subnotation, that tells you what term you are looking at. So if I have G sub 1, that tells me I am looking at the first term. G sub n, that tells me it's any term. I haven't decided yet. The n is in there because it can define any term. R is the common ratio like we saw, and n is the position in the sequence. For example, the sequence we have here, 1, 5, and 25. The first term is G sub 1. The second term is G sub 2. The third term is G sub 3. Let's start to fill in the information. G sub 1 is our first term. R is found by dividing the second over the first, like we saw earlier. It's the exact same process still. And now that I know that stuff, I can start to plug into the actual formula. Our explicit formula looks like this. So instead of G sub 1, I replace that now with the value we assigned it. Instead of R, I replace that now with the value we assigned it as well. Notice I did not know an n value, so that does not get replaced. So our explicit formula looks like that. 1 times 5 raised to the n minus 1. From here, all you need to do is plug in. If I want to find now the 12th term, right, that's what they're asking us to do, is what is the value of the 12th term? Well, what we can do is we can plug in. Notice instead of n now, that n value has changed to a value of 12. Once I plug in, I could type it into Desmos. If you type it into Desmos, you might need to include parentheses on the 12 minus 1 to leave it in the exponent. Or 12 minus 1 is also 11. You could just type in raised to the 11th into Desmos. If you do this correctly, what you would end up finding is a very large number in this case. You would end up getting 488,28125, 48,828,125. The same process can be done with these other ones as well. Some people don't like number 16 because the ratio gives them some decimal, but that is okay. It doesn't matter if the ratio is a decimal. You can still create your formula with that. It doesn't matter if it's negative. You can still create the formula. If I did do number 16, I would get something like this. Again, replace the n with the 8th term, and you could type it into your calculator, get negative 0.0061 and some other values. Okay? There is finding any term in the sequence using an explicit formula. The last thing we need to talk about is finding the sum. Realize sum generally means what is the total. What is the total found by adding the terms or whatever you're looking at together? Well, what they're asking us for first is what is the sum of the first 6 terms. Notice I have 1, 2, 3, 4 terms right now. I need the 5th and the 6th. Well, I could find the ratio first to figure out what to multiply by. In this case, it looks like we're multiplying by 2 between each term. So 8 times 2 is 16. 16 times 2 gives us the 32. Our sequence is now 6 terms. So what I could do is I could add each of those values together and figure out what that gives us. In this case, that would end up adding to a value of 63. This process, though, can get pretty extensive, because what if I needed to find the first 15 terms? I would still have to find another 9 terms, then add them. That doesn't seem very efficient. So instead, there is a formula that you can use. The sum formula here says, okay, take the first term, G sub 1. This is 1 in our case. Multiply that with 1 minus R. We said the R value is 2. Raised to the n. Remember, n is the value of the term. It's the term I actually care about. This is the 15th term, so I raise it to the 15th. All over 1 minus R, where again the R value is 2. We can use this formula just replacing the different parts. In this case, if you were to use those values, you would end up getting 32767, 32,767 is the sum of the first 15 terms. Thanks for watching. That is our 7.4 notes about geometric sequences.